Oh, hi. Welcome to another edition of the Tutor Wizard. And you're probably, yes, I got the stupid ears on, okay? I saw them sitting over here in the pile of, well, Mr. Dressup, Canadian reference. If you're not a Canadian, you probably aren't digging it, but this is the equivalent of the tickle trunk. And you can find all kinds of interesting things in anything called a tickle trunk.
The
I don't
tickle
know.
trunk means something else on White Ave here.
Mr.
Yeah, well,
Rogers,
there is a
Eddie
tickle
Murphy,
trunk
Eddie
here
Murphy
in
version of
Edmonton
Mr. Rogers.
that has adult entertainments. How about that? That works for me. Anyway, I don't know. What about this ears thing? Is this working for anybody, or should I just ditch them?
No, leave them. Leave
You
them.
think?
You've committed.
I'm looking at the little monitor. I can see what's going on over here. It's not like I'm looking off at some. The peanut gallery's that way. This is just the online monitor. So anyway, welcome again to another edition of the Tutor Wizard. Um, your regular host, Adrian, is currently engaged in a video game. Oh, you'll probably hear him in the background, especially when he gets killed. Today, I thought I would write like that. See, I'm going to continue some more statistics commentary. Regular lectures are pretty much wrapped up. I had some students earlier in the week. We talked about simple linear regression and correlation, but in a very abbreviated manner. So I'm going to expand a bit on that today for their benefit and your benefit. And that's usually how the first semester around here wraps up. I always tell people that if you're going to do a second semester in statistics, these topics are going to come back to you with pointy teeth, especially when simple linear regression transitions into multiple linear regression. Now, I'm just going to wing it again today, so I'm going to try to pick the numbers. They're going to be useful and easy to use. Occasionally, we may have to do some arithmetic on the board, but yeah, we'll play it by ear. Okay. I'm, uh, I'm rambling, and I'm not doing stuff, so let's get busy doing stuff. So the topics today are the correlation of Mr. Pearson. We'll start with that. And then we're going to segue into simple linear regression. We won't take it right from raw data. We'll start with some descriptive statistics and then produce the simple linear regression equation from there. And in the theme of trying to survive the final exam coming up, we'll probably look at some typical exam questions. I'll probably miss one or two. I always do. Whenever I look back at these videos, it's always, I wanted to talk about that. I forgot. But we'll try. We'll get at least 80% coverage, maybe 90%. If I get a good day today, it'll be 100% coverage. So let's erase this stuff and get this show on the road. All right. You can go away. Now, the formula sheets that we typically use around here, this stuff is under the heading on your formula sheet called bivariate data because you got X and Y variables. That's typically the nomenclature, but you have an independent or explanatory variable and you have the dependent or the response variable. And there's got to be a relationship between these things if we're going to have a useful simple linear regression or if there's a useful correlation. So that's what we're going to explore first. Now, what do we know about correlation? Well, let's write a few things down instead of my just rapping on here. So the symbol that we're using for correlation, if we're referring to the sample correlation, the correlation that you've computed, this is lowercase r. And as with everything in statistics, the sample produces a statistic which is then used to estimate the population parameter. Remember, you can't know the population parameter unless you actually measure everything under the sun, or in the topic anyway, what you want. Anyway, so this thing estimates the Greek symbol rho. So if you have an exam and the instructor wants to make it a bit more complicated, they'll say something along the line of, using the estimated value for the parameter rho. They might just put rho on there or whatever. But remember, the Greek letters refer to population parameters, typically in courses like this. Now, what do we know about R? R is never bigger than +1, never smaller than -1. And I'm going to make a number line on and talk about this in some fair detail, actually. We'll even I was debating the other night when I was thinking about what I was going to do for the next stream. Should we go really hardcore and do this, the more detailed computational formulas for this? I don't think we're going to do that today. Mostly at a sense of let's not be cruel. Although some days I do miss the, oh, let's do it all with summations. But yeah, it's not where the course is going, and I don't want to scare anybody off. So, all right, so we know R lies between +1 and -1. I'll tell you what those things mean in a minute. R is not a percentage value. Okay? R squared is a percentage value, but R itself is not. R has no units. So we never say a correlation is 0.65 kilograms per whatever, because we don't do that. It's just a number. What does the number represent then? Well, the number then, and this is the definition. There's going to be a lot of definition questions on the exam. So here's your first definition of many today. R measures the strength of association between two variables. Okay? Whoop, there's an S on that. Okay. So that's what it does. It measures the strength of the association. More to come when I make the number line. But at the end of the day, as you get closer to +1 or -1, the association or the correlation is stronger. Which means at 0, there should be no correlation whatsoever. Problematic, of course. Talk about that in a bit. All right, so this is a couple things to keep in mind. Oh, I got one more. R is also bidirectional. And yes, I can say that. How do you spell direction? Bidirectional.
We need to start doing spelling tutorials.
I never said I was good at spelling. So if I say to you that X is correlated to Y with the strength of 0.70, you could say back to me, well, that also means that Y is correlated to X with the strength of 0.70, and you would be correct. It doesn't matter the order. So if you're on a multiple choice or a question where you have to talk about this, don't choose the option that's, oh, well, if I'm going from X to Y and it's positive, then from Y to X must be negative. No, 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 don't do that. Don't do that. It's not true. Now, I've got a few more things to say about this, and it's probably best that we say it with a number line. Let's do that. Zoom. You know, I really do enjoy using the chalkboard far more than I enjoy using the whiteboard. There's something very organic about using chalk. Whiteboards seem to be messy and, well, they're chemical. At the end of the day, it's a chemical. This is a mineral. That's not a mineral. That's a mineral. Let's see, you played knifey mineral before, right? Simpsons episode, Australia, knifey spooning. Go look it up on YouTube. All right, let's make a number line I was talking about. Here to here. And we'll have 0 in the middle. So this is -1.00. This is 0.00. And this is +1.00. That's supposed to be a 1, by the way. There we go. All right. What do these particular values mean? In general, if you're working with data and you get +1, -1, or 0, you've screwed up. It shouldn't happen. But usually it means you've done something wrong with data entry because you're probably going to be using software for this. So why am I saying that these are screw-ups? Well, let me show you why. At -1, you have perfect negative correlation. Okay, well, what does perfect negative correlation look like? Well, it means there's your line of best fit, the simple linear regression line, And to get negative, well, there's a couple of ways to get perfect correlation, but the idea is there's really no, the dots represent observations, and the line represents predicted values. So if you have perfect negative correlation, there's no difference between observation and prediction. Which means, why are you doing simple linear regression? If you know this pattern, you can make perfect predictions. Well, why are you studying something that you can predict perfectly? It doesn't make any sense. The negative sign on correlation, by the way, simply means that as x increases, y decreases. That's all it means. It's not a negative in the sense that it's bad. It just tells you how things change, how one variable changes in relation to the other variable. So perfect correlation says, if I know the change in x from, say, x1 to x2, I can tell you exactly how y1 changes on its way to y2. Why would you do that? You're wasting your time. So usually this happens when you, if you're using software, you just probably set the variables up incorrectly. Okay, enough of that one. Let's go over here. What about perfect positive correlation? Well, it's the same thing. Perfect positive correlation, then, as a scatter plot, simply means the line increases from left to right. And again, we have observations and predictions that line up perfectly. This just means that as x increases, your y value increases. And again, if you know the change in x exactly, then you know the change in y exactly. Again, kind of gets in the, doesn't really make sense in the sense we do statistics so that we can make predictions about things that are inherently variable. And there's no variance here. That's just whoosh, where you go, right? All right, what about this thing at 0? If you get 0 correlation, you've probably done something mathematically wrong. Because if you look at the formula for correlation, which is the covariance of xy, we'll talk about that in a bit, divided by the variability, or the standard deviation of x and the standard deviation of y. To get 0 here, this has to be 0. But if the covariance is 0, well, how do you get that? You'd have to have some seriously contrived data to get a 0 in the numerator here. Without, no, one of the ways covariance can be written is the sum of x sub I minus x bar times y sub I minus y bar. Well, to get 0 here, no differences. This stuff all has to add up to 0. So something's gone wrong. That's my point. Even if things are, maybe there's actually no correlation whatsoever between what you measured. You know, it's like, oh, was there an earthquake? The correlation between earthquakes and, say, the phase of the moon. Well, you could probably say, but it's gravitation. Okay, how about the correlation between whether I'm wearing these stupid ears on my head or not and whether there's an earthquake? There should be 0 correlation there. But mathematically, you're probably going to get some little fractional number. So the point is, this means you've done something wrong. So these are the edge cases. Go and review your data. Check the boxes you ticked on SPSS or in R, what command line commands you entered. Something's gone wrong. All right, let's get rid of this. Oh, I don't want to get rid of this part. I want to make one more comment about this. Because the role R plays in constructing the simple linear regression equation, or the mathematical model, this looks like this. Here, R is 0. They're having fun over there. The peanut gallery is busy playing, I think it's Mario today. This means the slope of the regression line is flat, horizontal. It's 0. And that means that there's no predictive power. So what does that mean? It means if x changes in either direction, y changes in either direction, but we can't make any predictions better than simple guesswork. There's no predictive value here. Which is why when we do second semester statistics, one of the things we do with simple linear regression is we do a t-test to determine, is the slope significantly different from 0 or not? because if it's not significantly different from 0, then we have no predictive power, and our regression equation fails the model utility test. We used to do that in this course, in 151, 161, and 141. We used to talk about that, but now it's all been moved up. Okay, so that was r is equal to 0. This is r is equal to plus 1. This was r is equal to negative 1. Anyway, these are the edge conditions. Let's talk about the real things we want to worry about. Now, the numbers I'm going to put up here are generally accepted values. Depending on the domain that you're studying, in whatever you're applying the statistics to, these numbers will probably change. In a tightly controlled experiment, numbers will be different. In an experiment or a study where you're using people and people are highly variable, the numbers will be different. But as generally accepted useful numbers, we have the following. The region for weak correlation is from 0 to 0.5, positive and negative. Mild correlation is from negative 0.8 to negative 0.5, and again over here, same thing with the positives. It's only once you're bigger than 0.8 are we in the zone of strong positive or strong negative correlation. Okay, there we go. Now, what do these look like? I'm going to give you a loose interpretation of how you can kind of judge visually a scatter plot and make an estimate of what the strength of correlation is. There's lots of things, different characteristics in the data that go into producing a value here. So this is certainly not complete. It's certainly not definitive, but these are loose guidelines, all right? And keep that in mind. They're loose guidelines. I'm not claiming that this is the be-all and end-all of visual interpretation. There's a lot of experience goes into it. Let's talk about strong negative. So again, we have negative correlation, and it's strong, so certainly the slope is not going to be 0, and it will be in the, as x increases, y decreases. But generally speaking, the data points will be clustered around the line of best fit in a fairly tight cloud. So if we call that an ellipse, the ellipse of the data will be consistently close and fairly narrow in width, laid over the simple linear regression line. Okay, so this might be r is approximately negative 0.9. Okay, so the predictive power of this is pretty good. If this was a topic of subjective probability, I would say, well, I'd be willing to bet my money, not your money, I would be willing to bet my money on some outcome. So one of the other ways to think about it, how much variability is hiding in here? Well, look how wide this is. That's pretty narrow in width as far as the y variability goes. So again, the predictive power is pretty high. If I know that x changes a small amount from, say, here to here, this is the variability in the change in the y value. Well, that's pretty good. Well, what about strong then? Well, strong is pretty much the same thing, except we have this way. So this might be r is approximately 0.90. And again, we're going to have a fairly tight ellipse around there. Here, x increases, y increases. Variability is fairly narrow for y values, which means the prediction variability is fairly narrow as well. Remember, in statistics, small variable measures of variability are kind of what you want, because when variability is wide, predictive power is weak. Now, how about mild? We're going to put that, let's put mild down here. Okay, again, it's still negative, and the slopes aren't going to be exactly the same, and that's not the point. It's not, sure, the slope might be getting a little bit closer to horizontal, but remember, in the slope formula, which you haven't seen yet, there's other things besides just r in there. There's also standard deviation of y, standard deviation of x to create an equation. But what we're going to have here is that ellipse containing the cloud of data points is somewhat broader, like this. There's much more variability here, which means the predictive power of our x variable is less than what we had here. So again, going my analogy about subjective probability of betting money. So while I'm willing to risk my money on a situation like this, I will borrow 20 bucks off you to bet on this one because this is more risky, because the variability is higher. So this might be r is approximately 0.7, give or take, whatever. Yoink, let's do this one over here. Again, much the same. Oh, that's not right. Let's get this right. There we go. So again, we got a fairly broad ellipse, the cloud of data, like so. Same comments apply, only thing is now as x increases, y increases. So that just leaves weak. Well, what does weak look like? Well, let's, I got room here, I can make them both fit. Let's do this one here. So what is weak negative correlation? Well, now our cloud of observations is a fairly broad ellipse. Much more variability on the y values. X is increasing, y is decreasing. So the trend I want you to take from these pictures is, as we go from weak correlation to strong correlation, regardless of whether it's mild, or pardon me, regardless of whether it's positive or negative, the y variability is decreasing. The cloud that describes the ellipse, that describes the observed values, is getting much more tighter as we move higher and higher towards negative or positive 1 for correlation. So this one here might be r is negative 0.2 or something like that. Now, you know, like I said, these are very general comments. There's other things that go into, you know, the final calculation, but that's considerably beyond where we need to be chatting about it today. And of course, if we come down here, for the sake of completeness, we have that. There we go. Now, what does zero correlation look like? I didn't make an ellipse for zero, but here's one of the things. So if we have r is equal to 0, and we do, there should be really no pattern in the ellipse. The ellipse, in a perfect world, would be a circle. There's no pattern to the data. This is why there's no predictive ability. If there's no pattern, you can't make a prediction because you can't model the pattern. Hence, r is 0. There it is. So that's the essence of correlation. Now, how do we compute that? And then we still need to mention r squared, the coefficient of determination, which I'm going to do here momentarily. So let's get this out of here and talk briefly about how to compute correlation. Oh, someone's got his guitar out. Okay, so r is the covariance between x and y divided by the standard deviation of x and the standard deviation of y. So they have to give you these summary statistics. Old-timey days, we used to compute them. Not anymore. This chalk's had the biscuit. Whoops, drop the biscuit. I'll use this piece of chalk. All right, so if I say to you s sub xy, remember this is the only one that can be negative and the only one that can be 0. So we could say then this is the only one that can be a value between plus and minus infinity. Why am I using close brackets on that? I almost think I didn't know what the heck I was talking about. There we go. So there we go. Now, let's say this is negative 50. And the standard deviation of x is 10. And the standard deviation of y is something reasonable. I don't know. Why don't we call it 8? Okay, what do we got? Well, then r is negative 50 divided by 10 times 8, which is negative 50 over 80. So r then is negative 0.875. What am I doing? 0.625. There we go. And that's what there is to finding that. So this is one of the formulas that are on the formula sheet. There is a funky formula on the formula sheet. I'm just thinking about the ones that my U of A students are going to see, which is the standardized x value times the standardized y value and n minus 1. Don't use this, okay? Just ignore it. It's on the formula sheet as a historical artifact. It needs to go away. Are you looking for stuff?
I found a tensor analysis book I'm trying to dig out of here, but there's cats I have to move.
Okay. Only thing I know about tensor analysis is if you want to understand Einstein's work, you better understand tensors.
Yes. His are two covariant tensors.
Okay. Okay, well, that's a topic for later. We're doing statistics.
Hurry up, I'm ready.
Well, I'm not. Are you chomping at the bit?
Yeah.
Adrian's chomping at the bit. I haven't even
He's
got...
going to come and stand and watch you like this.
You could always wear the ears, you know. I'm really good at tuning people out too, usually, so you could stand there all day. I'll just hip check them out of the way.
Yeah, my grandfather always claimed he was deaf. He could hear me just fine. He couldn't hear his wife at all.
Critical commentary from behind. All right, r squared. Let's get this out of the way. I don't want to forget about this one. So what is r squared? Well, this is the coefficient of determination. And this is going to be on your exam. It is a percentage. That's what it is. So if r was 0, let's say negative 0.4, that's the final result, 0.7, then r squared is 0.49, and we interpret this as 49%. Okay, so it is a percentage. Yeah, percent value. Now, that's not its definition, though. The definition is the thing you're going to be tested on. The definition of r squared is the percentage of variability in the dependent variable that's explained by your choice of the explanatory variable. That's it. So the example that I always use is when you're talking about fuel economy in vehicles, and I'm basing this on an old study that I have stuck in my head, which is infinitely better than an iron spike, but sometimes, you know. The r squared value for the study I'm thinking of comes out around 40%. It says 40% of the variability in fuel economy on any gasoline engine is explainable or can be attributed to the size of the motor. There's a lot of constants involved. I mean, you have motor size is, you know, the volume of the cylinders, so that determines the amount of air that and fuel mixture that has to be pulled in every stroke of the piston. And that's not going to change. Of course, the fuel might change a little bit depending on the tune of the motor, but the point I'm getting at is 60% of the variability is attributable to other factors. It could be who's driving the vehicle. Are you running on smooth, new pavement? Are you on a rough gravel road? All of these things also contribute to the variability in fuel mileage. And there's nothing you can do with that with simple linear regression, hence the switch to multiple linear regression where you can have more explanatory variables. But that's how to interpret this. So it is, I'm going to write that down. I don't get rid of this. It is the percentage, so this is just shorthand, percentage of variability in the, I'm going to just say y variable, under the understanding that y is typically the response variable, explained. You know, I'm happier if you guys are busy doing stuff over there. Go play a game or something. You can ignore me. Explained by the x variable. There we go. There's your definition. You'll get tested on that. If you're not tested on that, you're, well, I don't know. I can't really imagine a final exam without that definition. Just like R is the strength of association between two variables. That's a fundamental definition that you really need to understand if you're going to do any more statistics, or if you can even use statistics. All right, that's it for correlation. Now when we segue into simple linear regression. All right. So ultimately what we're trying to do is work with a scatter plot. Let's get some names associated with the players on the field here. Now there's our x-axis. Typically this is your independent variable. Here's your y value, or your y variable, your response variable. And we usually have, well, what am I saying usually? Where we always have a line of best fit. I'll make it a positive one because that's a habit. So this is our mathematical model, y hat, so hat means you computed this thing, is equal to b sub 0 plus b sub 1 times x. And your prof may call those betas, and if your prof is from Europe, they probably call it beta. Call it something. So this is the useful model. So this model estimates the population model, which is just y is equal to capital B sub 0, capital B sub 1 times x. This is the one you want. So we have to talk about how to compute B sub 0 and B sub 1, but we're going to get to that. So that's what this line represents. And if the line actually goes through several points, consider yourself lucky, but really it's the prediction. So what are we predicting? Well, we're trying to understand the relationship hiding in patterns of the dots. The dots are observed values. Each one is an XY pair. Now, observed, predicted. And there's a difference between the two, which is called a residual. And the formula I'm going to write down here in a moment is not on your formula sheet. What is a residual? How do you compute the residual? So the residual, RESID, is equal to the observed value minus the predicted value. In other words, y sub I minus y sub I hat. And if you've computed this correctly, here's another residual. Observed is larger, predicted is smaller. This is a positive residual. Here the predicted is bigger numerically than the observed. This is a negative residual. If you've done everything right, that thing should add, the sum of all the residuals should be 0. If it's not, something's gone wrong, generally speaking. All right, but remember, this formula is not on the typical formula sheet. Now, what else can we say? Well, I'm not really thinking, we don't need to speak too much more about this. Oftentimes, well, here, let's do this. So here's the range of x values involved. So yes, there's a y-intercept here in this symbol, but typically that would be if we were to extend the line. But our mathematical model is only valid between the minimum and maximum input values that was used to construct the model. So the reason why we don't physically extend the line is we would be extrapolating in this direction. And again, we could be extrapolating in that direction, but you don't want to do that because the results are unpredictable or unreliable. So we'll encounter a question regarding that in a minute. Now, what else can we say about this? I think we've said enough about that. We got the residual comment up there. We have a difference between prediction and observation. We call them residuals. There's the formula for it. We have our model formula. It remains for us to compute the y-intercept and the slope. And I keep thinking I'm forgetting something here, but we'll see what comes back. We can always pop it in later if I remember what it is. Let's do that. So there's only a couple of formulas for this topic. We've already seen some of them. R is covariance x sub y over sx and sy. So remember, this is standard deviation for x values, standard deviation for the y values, and the variability when x and y are taken together. Now, b sub 1, the slope. And for you calculus rats, that's a derivative. But this is computed by r times s sub y over s sub x. And the intercept, which is b sub 0, is the average value of y minus the slope times the average value in x. And if you are quick of eye, you'll notice that you have to do it in the order I listed. You need r to get the slope. You need the slope to get the y-intercept. Keep that in mind. And we're going to do this just using summary statistics, and we'll do a couple of examples, and we'll go from there. So let's do a quick and dirty one. So let's say that the covariance is known to be 10. Standard deviation of x is known to be 2. Y's standard deviation is, let's pick something that's useful here. I guess we need something a little bit bigger. That's what she said. No, I had to do that. I'm sorry. 2 times 8, 16. Do I know what 10 16ths are? That's 5/8 again. Whatever. We'll use that. Okay. Now, we need y bar. Average value of y might be, 20. Average value of x might be 10. We'll keep it simple. And we know that the minimum x value is 5, and the maximum x value is 20. Okay. This is typically the numbers they're going to give you. They might give you some extras. They might even give you r pre-calculated. It kind of really depends on who put the exam together, but should always be prepared to have to do everything from scratch. Well, such that it may be. All right, so first thing we need is r. What is r? Well, it's going to be using this formula. So we need sxy, which is 10. The standard deviation of x is 2, and 8 for the standard deviation of y. So this is 10 over 16, which is 5/8, and it's 0.625. Okay, that's pretty nice. We can work with that. I'm just going to write a 5/8 here just so I remember something coming up. Now we have r. Now let's get the slope. What is the slope? Okay, so this, I should have loaded, that's r. So here we have b sub 1. So we're going to have our value of 0.625. This is going to be multiplied by the standard deviation of y, okay, and divided by the standard deviation of x. So we're going to do this with fractions because I'm not using a calculator. So this is 5 over 8 times 8 all divided by 2. So this is 5 over 2, which is 2.5. So there's our slope. Now slope has a definition, and you'll probably get tested on this. I'll do an example of that coming up. Let's get the definition out of the way right away. The slope represents the expected change in y hat when you change the explanatory variable by 1 unit. You gotta be careful when I said 1 unit. Now, if the units are in 10 square feet, it's not going from 10 to 11, it's going from 10 to 20, because that's the unit. They'll specify that in the context of the problem. We're not going to get stupid with that. We're just going to do some stuff with this earlier, but I just wanted to point out to watch out for that little trick, or trap, I guess. Not so much of a trick as it's a trap. Okay, we got the slope. Now we can get the y-intercept. So the average value of y is 20. We know the slope is 2.5, and we're going to multiply that by the average value of x, which is 10. We get 20 minus 25, so we get negative. Ooh, that's an unusual number. I don't usually end up with a negative one, but that's fine, whatever. Well, you know what? I don't want to chase this. Let's make this 30. Sorry, I'm not trying to be a schnook on that. It's just that I don't want to torture people with something that's Well, how is it supposed to be negative? Just don't worry about it. We'll fix it. So this is going to be 5. All right, so there we go. All right, well, now what's our equation? We can put our equation together. Our value, remember, is y hat be b sub 0 plus b sub 1 times x. So that means our mathematical model will be 5 plus this one, 0.625 times x. Boom. That's all you got to do in this course. I need a new piece of chalk. That's a brand new one here. Let's see here. What do we got? Come on, you. I feel like a smoker or something pulling out a pack of stogies. All right, so there's the computations for this. It's not too bad.
You done yet?
Soon.
This is a really good book. Read the cover.
I can read the cover. It's an epiphany in blue.
Yes.
I thought it was funny. Whatever. I've never actually seen Adrian chomping at the bit. Actually, he does chomp at the bit a fair bit. All right. You ever think about how silly the phrase a fair bit is? Yes. What is a fair bit? Is it a bit that's blonde? I don't know. One of those old English sayings.
Trying to sell you a bit instead of a lot.
Well, it could be a quarter bit. I understand that 2 bits is old reference to 25-cent piece, a quarter, because if I understand the history of it correctly, a Spanish gold doubloon could be broken into 8 bits. So a quarter would be 2 bits, hence the name 2 bits is equal to 25 cents. Useless things you remember from your youth. All right, what are some typical questions we can run into here? Question number 1. Ooh, brand new chalk. It's almost sensual. Nobody's going to criticize that. Holy mackerel, I've been totally ignoring the chit-chat. Yes, I stole it. Yes, you're right, captured EV. All right, anyway, getting back to this. We want to estimate the value, ooh, squeaky, of y hat, I don't know, when x is equal to 15. Okay. I have no context associated with our mathematical model. I don't want to complicate things. I just want to show you how to do this. So a question that asks you to make an estimate or a prediction or something like that means plug the x value into the equation and compute it. That's all it means. So that means y hat will be equal to 5 plus 0.625 times 15. All right, what the heck does that work out to? Well, this is 5. This is 5 over 8. This is 15. Oh, that doesn't simplify. That's 75 over 8. So this is going to be 75 over 8. That's 9.375. So this is 14.375. Woo, there we go. How's that for fun times, good times? And you know, one thing I have noticed in the last few semesters is the computations they're going to ask you to do, by and large, not entirely every case, but are mostly user-friendly if you have to do it by hand. And why? Well, calculators, right? Some people invariably show up and think they're going to use their cell phones. No, you're not. So now you're left with a pencil and paper and your brain. Or you're going to use a calculator like a TI-34 or TR-84, sorry, or an 83. You can't use them because they're not approved. So you have to do it by hand. So to be fair to people, they oftentimes use numbers like I'm using here that are amenable to be doing hand computations with. Now, we could reverse this question, you know. I could say, for the second question here, is given that y hat is equal to, oh, I don't know, 20, what was the x value that generated 20? In other words, now we got to do a little bit of algebra. Well, it's not terribly hard. Let's do that. He said terribly hard and he hasn't done it yet. Let's see. So we got 20 is equal to, so we're using our model again. Remember, everything we're doing is based on this. That's equal to 5 plus 0.625 times x. We need to find what the heck the value of x is. All right, well, let's do that. So remember, this is 5 over 8. So I'm going to move this over here. We get 15 is equal to 5 over 8x. So that means I'm going to go 15 times 8 divided by 5. So this is 3. This means x was equal to 24. Woohoo! Piece of cake, as it were. Okay, what do we got going on down here? Okay. Hey, we got a new follower today, 2327. Cool. Welcome. I should have said something earlier about that. All right. So there's 2 questions involving some algebra. I have to hurry up here. I can feel the tension coming from Adrian. He needs to be up here. He's got nervous energy. Now, the things we don't do anymore in this course is compute confidence intervals and prediction intervals for this stuff, which I actually miss doing. That's kind of fun. But I got to show you a trap question. It's a trap. You darn right it is. Let's say, well, I don't want to change that just yet. So we'll do another one here for a minute. Okay, we're going to do this is question 3. Estimate y hat when x is equal to 1 and comment on the validity. All right, so if you just take this at face value, this is really no different than what we've already done. Y hat is equal to 5 plus 0.625 times 1, so this is just equal to 5.625. That's not terribly hard. It's the commenting on the validity of the computation that's going to get you. Recall that I said when I had the scatter plot up here earlier that the mathematical model is only valid within the range of the inputs, which is why I wrote this. The minimum x value for the xy pairs was 5. The maximum was 20. I'm using a 1. I'm extrapolating. So while you can mathematically produce a number, it's not reliable, probably not even valid, as you don't know how the curve, the straight line, is going to behave outside the range of the inputs. So don't do that. Pretty simple. I'm going to do one more example, and we'll turn this beastie over to, actually we could do 2 more examples. I want to do, actually, you know what, I'm going to set up something a little bit different and talk about it, and then I'm going to turn this over to Adrian because I'm sure he wants to do some stuff. So we're going to get rid of this. I'm going to re-specify some information. So one of the things that they're going to do is give you table output, usually from SPSS, R, or Excel. Those are typically the programs that they use tables from. I'm going to model just the pertinent information from a Excel table. So you got this. You have, I don't know, pick grammar. Grammar? What's grammar? So this will be the coefficient column, and there'll be a bunch of stuff here, and we don't really care about that. And this will be I believe this is labeled constant. And this will be, this would be, I think this is labeled coefficient. And there's a name for this, can't remember. It's got a name. Okay, name. So this might be 10, and this will be negative, say, 3. And you may also be told that r squared is equal to 0.64. And they will tell you to, okay, well, some of the things they may say is, while using the information in the table, construct a simple linear regression equation and do something with it. Well, the constant, the first row is always your y-intercept. The second row is always your slope. So then we can say that y hat is equal to 10 minus 3x. Okay, that's not really what I wanted to get at. Here comes the crux of my point I want to make. The next question is, what is r equal to. Now I gave you r squared. Okay, well you know that if r squared is square rooted, you get r. And that means the square root of 0.64 is actually 0.80. And the thing is, this will be one of the choices on the multiple choice answer sheet. And this is wrong. The reason why is the sign on the slope has to match the sign on r. And you can see that if you recall that the equation for the slope is r times s sub y over s sub x. So these can't have different signs. Watch out for that. If you have a negative slope, then r has to be negative. And I guarantee you, many people will get this wrong because it's an exam. You're in a hurry, you're thinking about getting it done, and you're going to go, there's the answer. You're going to go check it off on the bubble sheet, and game over, baby. Okay. Have I missed anything? Oh, I'm sure I have. There's other questions we could do that are quite interesting about this. Oh, I got one more. We're going to use this example, and we're going to compute a residual. But actually, no, I'm not going to use this. This is kind of stupid numbers. Let's do this. So the price of a new car, nothing unique, or the price of a car is estimated by 25,000. Ooh, let's let's do it this way. Minus 2 times age. Yeah, let's not do that. We'll put 25,000 down here. I have a couple of exam, what's the word I'm looking for, review sessions coming up that I want to do, so we will talk about more of this in detail then.
Levitate Tato.
I know he wants to get on here, so okay. So the price of a car is $25,000 minus 2,000 times age. In context of something like this, how does residuals tell you something? Well, generally speaking, what we're going to do here is talk about the use of the blue book or the black book or whatever you want to color the book. So let's say we have a scatter plot. Oh, that's the wrong slope. It's negative, like this. So here's age. Here's dollar dues. Cars get older, they get cheaper. So let's say somebody with x value equal to 3 paid $18,000. I don't know where that goes actually. So at x is equal to 3, actually, yeah, that's right. We can do that. That'll work. I just had to do that in my head. So this is the $18,000 price point. And this is the formula. Did they overpay or underpay? Let's find out. So the price is equal to 25,000 minus 2,000. Car is 3 years old times 3, so this is 6,000, so this is $19,000. So the predicted price of the car is $19,000, but you paid $18,000 for it, so this residual says you got a deal. You paid less than what the car's book value was, which either means the car was a good deal for you or there's something wrong with the car. This is a contextual question that may show up on an exam. They'll ask you, what does this residual mean? So if you're not sure, you can figure it out. Now, the last question we're going to do is useful advice about slope questions. We'll leave this up here. Let's say we know that a 3-year-old car has a value of $19,000. Okay, I'm in a hurry, that's why my handwriting has gone to hell here. $19,000 redues. What further depreciation Why is that hard to spell? Depreciate. Help! What further discount? There we go.
D-E-P-R.
That's okay. I've already changed it to discount.
D-I-A.
M-O-U-S-E. M-I-C-K-E-Y. M-O-U-S-E.
spell sex to 16-year-old girls without friendship bracelets. Ha ha!
Oh, stop that there, Goofy. You're being a bad, bad dog. Okay, this is just getting stupid. This is getting very out there. So what further discount is expected
You wear the friendship bracelet if I say ha ha!
if the car
That's from South Park.
was
Ha ha!
The Jonas Brothers.
5 years old?
Yeah.
How am I supposed to sell sex to 16-year-old girls? Ha ha!
This is getting out of hand. I think it's the ears are squeezing on my brain or something like that. All right, so there's the simple way to do this is to simply recompute with the value 5 instead of the value 3 and subtract the difference. And because this is just a simple example. But because the slope is defined as the expected change in the y value, so here the expected change in the price, if we make a unit change in the age of the car, we can do it just with the slope. Here we have a 3-year-old car. Here we're talking about what is if it's 5 years. So the expected change in age, I wrote delta age is -2. What is the value of the slope? Well, the value of the slope is $2,000. So we have 2,000 times -2. So that's going to be a further $4,000 discount on the price of the car if the age goes from 3 years to 5 years. Typical exam question. All right, I'm going to stop talking now. Are you ready to come over here, Mickey? Oh, Minnie! Nothing?
A
No?
little bit further, a little too far, Minnie.
All right. How'd I do? How long did this little Oh, an hour. That's usually about how I can usually do this lecture in about 50 minutes. That one worked out all right.
Math check.
Okay, you guys are having a conversation on here. Indeed. I totally missed all that because I was sort of locked in and doing a lecture on correlation and simple linear regression. So I will, Adrian's busy looking for something. I was going to point out that we're going to do exam reviews coming up because it's exam season, and we would like very much your support on Patreon. And the link is going up. Thank you, Lorenzo. Lorenzo's our producer in the background. So I've got a stats review book up there with 220 practice questions with complete solutions, you may notice, which is highly relevant for anybody in 151 or 161. Nudge, nudge, wink, wink.
And there's a calc book.
And I have a calculus book up there too, again, for just basic first semester calculus, nothing fancy. There's a few tricky questions in there, but basically if you're not sure and you need practice material with solutions, those are your go-tos. Now, the business of Patreon support, YouTube don't pay worth anymore. A pox upon YouTube, although we're still going to use their platform for now, but you know, they're generating income and not really sharing much. I've noticed, like I also follow, like I've mentioned in a previous video, like I follow a couple mechanic channels, and Electro Boom, I watched him today, had a new one out. Big Clive likes to do electronics. These are my usual spots I go to, and I notice all of these people support their channels now through either PayPal and or Patreon or actually membership on the YouTube channel. We're not big enough to have that, I don't think, but we do have now a Patreon account. And yes, I know I'm begging, but I have to because bills need to be paid, and donkeys need waffles, and Adrian needs this microphone.
Yes, I do.
All right, what you got, big guy?
I found all the evidence of how cool I was when I was a System of a Down, Slayer, Slipknot,
Oh, you found your concert
Tool,
tags.
Megadeth, Les Claypool, the Mars Volta. I found the Mars Volta one.
Well, don't run away with that. I was going to say, Rush is touring again this year, and they're coming to Edmonton.
Who's drumming for them?
A German girl named...
Yeah, she's good.
Yeah, oh, I saw her on a clip from the Junos, and I'm going, you know what? Good choice. So it's Rush at 50, and there's not a
I
lot
was
of
like,
bands around there like that.
Girls play drums? What?
Well, yeah. I'm not going to make any of the obvious innuendos because... Oh, what's that? Where's the microphone?
No, I'm putting it on my shirt. Kitty!
Come here, good timing. Hi.
It's little kitty.
Little kitty.
So, the definition of the word innuendo, since Lorenzo's Italian, he'll appreciate this. An innuendo is an Italian suppository. There's your dad joke of the day. Done.
Oh, kitty. I found a kitty. Hi. You're good timing. You wanted to go hang out with them? Okay, here.
Okay.
It's the boy. No. What does that mean then? You want food. I know what that look is. Kitty, come back here. I love you. Come back here. We're gonna do some math. Yeah, you want to go up there? What's up there? Oh. There's that thing. It's like, I don't know what kind of religion this is, but I want in. Where they're just holding up a cat. They're praying to a cat. I don't know what religion that is, but I'm in. Okay. I know. Oh, I know. Just don't pick you up. You're a good kitty. You're just gonna stand on my legs. Does that mean you're hungry and you want food? I know. I don't think so. Oh, he's gonna scratch his ear. I thought I.
Do the Meow Mix song.
Meow, 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 meow. Let's see if we can get him to stand there for a minute. Oh, good kitty. Here's a kitty. Meow, 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 meow.
Nipples and clits. I'm going to get me some nipples and clits. I made that one up. I was so proud of that years ago. Never get to share it with anybody because most people go, ew, what are you talking about?
Hi. What do you want? I know. We're having technical cat difficulties. I'll be right back. I'm going to go feed him. Meow, 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 meow. Meow, meow, meow.
Alright, your mic's back on.
Oh, I was going to leave it on. I was talking kitty talk. Meow, 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 meow. He muted me because I was like, I'm going to talk about those two jerks while I'm upstairs to the cat. They don't really love you. I'm the one who loves you. What was I doing? Oh. So primitive Pythagorean triples. Last time what we were doing was we have a squared plus b squared equals c squared. Classically, that's the sides of a triangle, which is right. And we're looking for, this is the Diophantine equation. So this is nonlinear Diophantine. And what that means is nonlinear should be obvious at this stage. We have more than one variable in each of the terms, a squared and b squared and c squared. Anything that doesn't have power ones is going to be nonlinear essentially. And then Diophantine means we're looking for solutions in z cubed, z positive cubed, which means a and b and c. C will make the hypotenuse. And what we're looking for is all of these are going to be in z plus cross z plus cross z plus. We're looking for positive integer solutions of this. And then you can find all the rational ones by multiplying by d, where d is in q. And that will give you all the rational Pythagorean triples. So what that means is when we're looking for this, we're looking for all the solutions. We don't want to miss any. And so last time we showed a clever algorithm for starting with any even positive integer larger than 1 that's odd. We can find infinitely many Pythagorean triples. Starting with any even number which is larger than 2, we can find infinitely more. Some different, some of the same Pythagorean triples, but then we find a Pythagorean triple, I believe 20, 21, 29, which can't be found in either of those lists. So somehow we're missing them in some sense. So there's solutions we're missing. So it's not the complete solution of the Pythagorean problem. And then this is thousands of years old, this problem people have been working on. And so what we want to do is talk about primitive ones. And so now, I think last time I started this, we're going to use the unit circle, and we're going to use the point, because I stole it from that book, some book, I don't know, I don't remember now, but we're going to use point -1, 0. And then what we're looking for is, we want the m to be rational. And so we're looking for the rational parameterization of the unit circle. Essentially, what we're going to do is close bracket. We're going to start with this. If this is the point, then we want another point AB. And what we're going to do is look at, so first of all, where does this rationalization come from? How do we get from the triangle to the circle? First of all, we could divide both sides by c squared and get this. So solving this is equivalent to solving this, and now because a and b and c were all integers, these are all rational numbers. A over c is a rational number and b over c is a rational number. So what we're looking for is, and then we'll make a one-to-one correspondence. What we're going to do is, if m is rational, the slope, which he was talking, he means Tim. If I say the disembodied voice, I mean Lorenzo. Yeah, that one. That's the one. I know they can't hear you. I can hear you. I'm hoping that they believe that there's people behind the curtain. Otherwise, it's just the Wizard of Oz. There's nobody there. There was somebody there. There was somebody there. All right, so now what we're going to do is try and argue that there's a correspondence between the rational parameterization of this unit circle, and there's a one-to-one correspondence between lines through this point and this point, arbitrary points A, B with rational slope, and the unique points with which have 0 less than m is less than 1. And so what we can do is, then that will generate all the Pythagorean triples. Let's see if I can just do this without any reference. So the first thing we're going to do is, we're going to do some long division and a couple other things. How do you get, what I want is the coordinates of A and B. So whatever this is, we're going to get, if we know that we have slope m and we have a point -1, 0, can you use one of the avatars of a line? Which one would you use? They're not very inventive in their names. We're going to use the point slope form of a line. So because I have those, let's use the point slope form of a line, and that's going to say y minus 0 equals m x minus -1, or y equals m times x plus 1. I should have used A and B. Yeah, you'll see later. It doesn't matter. It doesn't matter. Now what we're going to use is, I'm on the unit circle also. This is x squared plus y squared equals 1. And so this is x squared plus y squared. I'm just copying it out again. Why didn't I do that? Because now we know what y is. Because these lines, I know what the equation of this line is through this point, and assuming that it has a rational slope m. I have the equation of these lines, but they're also intersecting this circle at another point AB. And so what does that do? That satisfies, that means that this equation of this line satisfies the circle's equations also. So in calculus, when we have this, two equations are equal when their equations satisfy each other. And so I'm going to put the y in there. That now gives me yx plus 1 squared has to equal 1. All right, I'm going to need some room here to do some razzmatazz. I should have moved that over here somewhat. It doesn't really matter. Just keep in mind that this is what we're doing. And everything, notice I'm relying on the geometry of the picture to make the flow of my argument concise. And also, I'm drawing this almost, even though we are live on Twitch, I'm doing this for myself, not for the audience. It's so that I can do this and make it seemingly like I haven't stolen this out of a book before, and I'm just raw dogging it and doing this but from scratch. But to keep it, the flow of what I'm trying to do consistent is I'm keep looking at the picture and seeing where we went from. So we went from the triangle we divided by this, and that put us on the unit circle. X squared plus y squared equals 1, where x is a over c and y is b over c. And then I want the rational parameterization of this. Now we have this, so let's make a quadratic equation out of that in a single variable. That says we have x squared plus m squared, x plus 1 squared equals 1. How do you solve quadratics? You expand everything and be clever. And I don't think we have to complete the square, but if we do, no, we're going to use long division instead and a clever trick to find these. So if you didn't know the clever trick, I'll point this out in a second. Let me expand this. X squared plus m squared, and then what do we have? We have x squared plus 2x plus 1 equal minus 1 equals 0. I tried. It's not as fun when you're listening, so we'll try to keep that down. We're not giving any sound warnings or trigger warnings. Suck it up, Buttercup. Sometimes the chalk makes a screechy noise. I'll try to minimize that. So now let's expand everything. We have x squared plus m squared x squared plus 2m squared x plus m squared minus 1 equals 0. Oh, keep this, factor this out. So then we have 1 plus m squared x squared. And then now that's, for lack of a better phrase, let's use capitals. That's ax squared plus bx plus c equals 0. There's a quadratic equation. Do you see it? It drastically looks different now, but the strategy is the same. This is what we're trying to teach. The thing that I would do is I have a quadratic. It doesn't matter what the coefficients are or what we were doing. Once you're in quadratic equation land, now you should have, can't I use the quadratic formula? Yes, the quadratic formula is derived from the completion of squares, which is always a funny question to me because I show how to complete the square even on the general one. They're like, can't I just use the formula? That means you have no meaningful understanding of what I just did because the quadratic formula is derived from completing the square on the general form. So if you don't cleverly see what I'm going to point out right now, which I stole from the book, is that I could just factor this by using the quadratic formula and find the two roots, the two youths. But because this point is on here, I know that x plus 1 divides this polynomial. So this has to be a factor of this. So let's do that and see that it actually does. If you didn't see it, you could just use the quadratic formula. Let me move this up. And then now we have to do some nasty, oh, I just erased it, crap. Okay, what we're gonna do is long division. I claim that x plus 1 is a factor of this polynomial. What was the polynomial? M squared plus 1 times x squared. That's a 1. X squared plus, what was it? 2m squared x plus m squared minus 1. Also, I'm making this look effortless, just like Connor McDavid does, but he practices every day, stick handling and all that stuff, so that when he goes on and performs, he looks like he didn't do anything. It was effortless. I did this calculation more than once. I did it on Friday, or I did it on Wednesday. What day is it? Today is Friday. I did it on Wednesday in between my classes of the 3 linear algebra classes that they made me do over and over again. I sat into this calculation. I did the calculation one more time, and then when I went up to feed the cats, it was on the table, so I looked at it quickly. I'm making this look effortless, but I'm cheating. I prepared myself. What do I have to multiply x by to get m squared plus 1 times x? This. Now we're going to multiply that together, and what do I get? I get m squared plus 1x squared plus, what do I get? M squared plus 1 x, right? Line it up. This got me last time. Subtract, that's why we did it. It looks nasty. Tim's following what's happening here. Oh yeah, so now what are we going to do? We're going to subtract, so that gives me 2m squared minus m squared is m squared, and then minus 1 x plus m squared minus 1. And do you see that's going to be really nice? Now what do I multiply x by to get this? M squared minus 1, and that will give me m squared minus 1x plus m squared minus 1. And then I subtract again. Careful to use brackets. And then that cancel, which means 0. So but that means it evenly divides. So now I have to do quotients. That's the remainder equals r. But what that says is m squared plus 1x squared plus 2m squared x plus m squared minus 1 is equal to x plus 1 times m squared plus 1x plus m squared minus 1. And so what does that mean? This is the AB that we were looking for. So what that says now is we knew this one, but we wanted the other non-trivial one. So I'm going to solve for x in this one. Yep. So what that says is if that's a root, what I want is now that means I have m squared plus 1x plus m squared minus 1 equals 0. And so now solve for x. This is the x that but this is the other point I'm looking for. It was on the circle, but then that means it's AB, which means a squared. Let's do this. Let's switch it to a and b now. And then I'll find the b coordinate in a second. Because that was on the circle, now what does that say? That says m squared plus 1a equals 1 minus m squared. And then divide by m squared plus 1, which we know is non-zero, because even if m is 0, which is a rational number, m squared plus 1 is not 0. So then that gives me the a coordinate of that new point that's in the first quadrant of the unit circle, the rational parameterization of this. So that's the a. What is b from this? B we can get because we know b was equal to ma plus 1. Or, see, I've switched it. No, I just permuted those two. That was the original equation of the straight line was mx plus 1. But now I want to match it to the ABC of the triangle here. So now what is that going to do? Also, yeah. I did a notation problem because I'm copying in my mind from the thing that I saw that I read. But let's do that first. What is that going to give me? So from here, the a, well, let's just keep it x and y and then, yes, we can. So x is this guy. What's y? Y is m times x plus 1. So, but now we know what x is. X is 1 minus m squared over 1 plus m squared plus 1. What do I do now? Get a common denominator. So I have 1 plus m squared over 1 plus m squared. I multiply by 1, dirty trick, cancel, cancel. And then that's going to give me what? A headache, probably 2m over 1 plus m squared. So now I have the y. So now what that said was the other non-trivial point in the first quadrant is going to be xy is now equal to 1 minus m squared over 1 plus m squared 2m over 1 plus m squared. And how does this relate to the Pythagorean triples? Now what we're doing is we're assuming that I derived this. I should have used p, q, and r. Whoa. No. Yeah, that's okay. That's okay. No, that was fine. I'm misremembering. I make mistakes sometimes. What am I trying to do? I'm trying to connect this calculation with all the primitive Pythagorean triples. But where does the P and the Q come from when I want to do this, when you see this on the internet? So M we're assuming is rational, which is P over Q. Q over P. Uh-oh. Q over P. Where 0 is less than Q is less than P. Why can I assume this? I'm going to spare you, but essentially what we've done is, or can you show me as an exercise, if M is rational, so is this. That's non-trivial. Or that's trivial, isn't it? because this point is also rational. That's the rational parameterization of this. So if m is rational, then so is this thing, because then we're going to put that in there, and then that's going to give it to us. And conversely, if these are both rational, the m is going to be rational also. If a and b are both rational, you can do the calculation. That gives us a bijective one-to-one correspondence between all the lines with slope m and the points on the unit circle in the first quadrant. It's going to give us all the primitive Pythagorean triples. So without loss of generosity, this is what we're going to get here. And now what do I have to do? The last calculation is, I really don't want to do it anymore. Math is fun, but sometimes the calculations are tedious. This would be the lemma. Well, I have to put the m into here, and then you'll get it. Just a second. This is the part where I didn't do it. I'm like, I'll just do that on the live stream. I passed the buck. So we're assuming the slope was rational in lowest terms, and because it's between 0 and 1, I can assume without loss of generosity. I keep saying that because it's an inside joke. Never mind. I'm not telling it to you. That because I had that rational parameterization, I can assume m is between 0 and 1, and because of that, I can assume that 0 is less than q is less than p. And that's where we're going to get all the Pythagorean triples from. Every single one. So I have to put this expression into here. So the a and the b, that's why I was going to switch the x and y to the a and the b. This is what we're finding right now. The a and the b, these sides, and then we'll find the hypotenuse by putting that once we know what a and b are, because we have a squared plus b squared equals c squared. So from this, what are we going to get? Let's do this. First of all, this says a is 1 minus q over p squared over 1 plus p over q squared. Can you simplify this now? This bop is going to equal what? P squared minus q squared. If you do the b, that's going to lead you to, you would get 2q over p plus 1 plus q over p squared, which will end up working out to 2pq. Oh, sorry, over let me do the calculation because now I've lost myself. I was going to be lazy and speed it up. This is equal to what? 1 minus q squared over p squared over 1 plus p squared over q squared. Now I'm going to do the same dirty trick twice. No, I just dyslexied. Put those upside down. Thank you. Q over p, if that's what you were typing. This is a plague upon my hissing. So this will be p squared over p squared over p squared. Oh, it does cancel off nicely, doesn't it? What did I do wrong? This is okay. There, yeah, that's why I suspected. That's why I did the calculation, because I'm already looking and cheating at the outcome that I have. Ugh, this chalk is going into my face. Let's speed this up. P squared minus q squared over p squared over the fraction p squared plus q squared over p squared. This cancels, so this gives me a is p squared minus q squared over p squared plus q squared. And then what do I have? A problem B is going to be equal to 2q over p plus 1 plus q squared over p squared, which is going to give me 2pq over p squared plus q squared. And those are on the unit circle. So that says that a squared plus b squared is going to equal these guys. I just erased them. But that's going to be p squared minus q squared over p squared plus q squared squared plus 2pq over p squared plus q squared squared equals 1. But then what does that say? Move this guy up. That says, there it is, there it is, there it is. Now I'm excited. See me being excited? Oh, we're going to sell this to the kids if we don't know how to do algebra, ha ha! That says p squared minus, yeah. I'm Donald ducking it right now too. I got no pants on. You can't tell if I do or not. Don't do the dance while you don't have pants on. We tried to tell him to go put pants on when he was upstairs with the cat. That's why I turned the microphone off. But he won't listen to me. P squared plus Q. Oh, squared squared. Do you see what that did? There's the Pythagorean triples. All primitive Pythagorean triples are P minus Q squared. 2pq, comma, p squared plus q squared, where 0 is less than q is less than p.
Nice.
There's all the Pythagorean triples. Oh, that'll get them all. That'll get them all. I said I would move this TV last time, and now there's blue chalk all over it. It's raining, man. Hallelujah. Sorry. That was just getting chalkier and chalkier. Now what are we going to do? I don't know. I was chomping at the bit to get that.
Give a shout out to Patreon, and then we'll see everyone tomorrow.
Yeah, that means Lorenzo's got better shit to do than to listen to me start getting into something else. Can I do one more thing? Shout out to Patreon, please. We're going to beg you. I don't care at this stage.
The link again.
The place that I work at, let's say it that way, is slowly getting rid of me because I'm in sessional purgatory and I have contract, and then when I use my loud, obnoxious mouth to say things that they don't like, all they have to do is not give me a contract next semester, and then I can't pay my bills anymore. So you'd be doing several wizards a solid by trying to help all kinds of, I'm going to guess, thousands and thousands across North America and Europe, tens of thousands of us poor sessionals that went and spent 15 years and got a PhD and now are just being abused by what is called academia. I don't think that's the way that they wanted me to say that. But shout out to Patreon. Can I do one more thing? Yeah. It might take me a few minutes. Okay. Here's a linear second order or linear Diophantine equation in two variables, x and y, or a and b. X and y, because I'm going to use a, b, c now. I should have used x squared and y squared, but the linear form means that every term has to be a multiple of a single variable or a constant. So classically, this is exactly what a 1/2 linear system would look like in linear algebra. Also, Diophantine. So this was the linear part. Diophantine means that we're looking for a x and y to be inside z squared. I can have negative integers now from this. We'll do Brahmagupta triangles on the Pell equation next time, which is x squared minus dy squared equals 1, which comes from several different places, including Archimedes counting the number of total cows in the world. They didn't have TikTok or the internet, and that's what he was doing in his spare time. I bet I could calculate how many cows there are in the world. I bet you can't, someone probably told him. And he said, F you, I bet you I can. And he did. I was impressed with this. Whoa, I'll show you this article that I stole this from. I laughed to myself. That's the first thing I thought. I'm like, why is he doing this? Because some bra came up and was like, bro, I bet you can't calculate how many cows there are. He's like, oh, I'm fucking take your gauntlet. I'll smack you with it. So we'll do that next time. Right now, let's show the difference between, do you see the chaos that was there if you followed all of my arguments, even though I was vague, on how to solve nonlinear Diophantine equations? Now what we're going to do is use the Euclidean-Bezusian algorithm. For close enough. Me fail English. You can't read what that says. Bezu. The Euclidean-Bezusian algorithm for finding greatest common divisors and how to systematically solve all linear Diophantine equations in two variables. So the first thing you do is, there's a theorem that says if the GCD of A and B, which we're going to call D, so I don't have to write all those symbols out in LaTeX over and over again. I can just call it D. G, C, D. Actually, probably because it's in mathematical things, I have to put backslash text so that it looks regular. G, C, D, close bracket, curly bracket, then a bracket. Yeah, so I don't want to do that. I'm going to call it D for simplicity. If D divides C, there's infinitely many solutions. And if D does not divide C, there's no solutions. None. None solutions. And so this is sort of the on-off. If you can get that the GCD divides this, and the first application we can do is in, what is that, Die Hard 3, where he's wearing that sign at the beginning. And then he finds Samuel L. Jackson because he's like, why are you wearing that sign? I don't know. But then they have to do the jug thing. So the jug thing would be a Diophantine equation. And so let's assume that we have solutions. So step 1 is if D is larger than 1, what we're going to do is reduce the equation. Also, why would that happen? Why would I want to reduce this? So if I have 8x plus 6y equals 12, I should have done this simpler. And I don't reduce it, equals 4. That didn't help me any. What's going to happen is, because I can do that, that's going to say the GCD is 2. So that's going to give me 4x plus 3y equals 2. And now can you find, if I put 4 times 2, I'm just ad hoc showing you why I would reduce. I'm justifying this to you. Oh, I got a solution, right? 2 and negative 2. But can 2 and negative 2 ever be multiples of 8 and 6? No. So if I hadn't reduced to this to start solving, oh, also, sorry, that should be an 8 and let's go back up to 6, but that'll be a 4. 16 minus 12 is 4, so it still worked. So do you see, by reducing, you don't lose the solutions. But if I hadn't reduced, I missed a solution. And just like the Pythagorean, the nonlinear one, the Pythagorean problem, we need all the solutions. So if you don't reduce, you might miss a solution, because these can never be multiples of 8 and 6. So you can't find that solution if you don't reduce. So step 1, reduce if the GCD is larger than 1. Reduce to, so what that says is A will be, the GCD will be P times D. B is going to be Q times D. And C will be equal to, because we're assuming that D divides C, that C will be equal to R times D. So now I can cut that out of this equation, because what that'll say is now it's going to be P times D and Q times D and R times D, and then I'm going to cut the D out of both sides by multiplying by, we don't have the inverse, but we can reduce it. This is the cancellation problem of the ring Z, because we don't have inverses. It doesn't have it's not a field, but we can still do the cancellation property. Step 1, reduce. Step 1, reduce. So now we get Px plus Qy equals R, where the GCD of P and Q has to be 1 now. Also, that's bad notation, but that means GCD without writing GCD. It's not an ordered pair anymore. So once I have this now, what do? I also can't get into it because Lorenzo wants to go home. So, but the analogy of this is the most, I'm just going to throw you under the bus because I'm not going to justify it. That's how you do it. Be quiet back there. The general solution, and this is the analogy that you're going to use whether you're doing differential equations or you're doing difference equations or you're doing the linear Diophantine equation. The general solution is the associated homogeneous solution plus a particular solution. That's a y. So I'm going to give you the method of solving this. The clever way to do this is commutativity in that same ring. So if I look, first of all, to find the x homogeneous solution, how do I do this? And that's why there will be infinitely many. The x homogeneous and the y homogeneous solution says that I'm going to do px plus qy equals 0 now. That's the associated. Homogeneous means you make the right-hand side 0. Once I do that, I can move one to the other side. Classically, I move y to the other side. And then now do you see how to find the solutions of all these things? By commutativity, if I make x equal negative q, and I make y equal p, that has to be true. And then I can multiply by any k in the integers, and that will also keep it true. So what that says is, there's my vertical solution. So that says x homogeneous is negative qk, and y homogeneous is pk. All the Hindus will laugh with me. PK, that means a little bit tipsy in Hindi. PK. It's also a pretty good Bollywood movie. Yeah, I've seen some Bollywood movies. So now we have the homogeneous solution. X homogeneous is negative qk, and y homogeneous is pk. And then this is also the Archimedes principle. There's no upper bound to this. Z plus or z. There's no lower bound either. Now I need a particular solution. That's where Euclid and the Bezusian and the mathematical magical table that I've got, that patent pending, is sort of mine, but I stole it from Andy Liu a little bit. But I 3M'd it slightly. I'll give credit to Andy Liu where credit's due. I don't know where he stole it from. All right, what does this say? The Euclidean algorithm says that I can find the GCD. When I do this, I'll just write it out generally like this. So first of all, what I'm going to say is I'm going to find the GCD of P and Q, and it's going to be 1. But what we're going to do is we're going to get P, assuming that without loss of generosity, P is larger than Q. Yeah. What we're going to do is we're going to get Q1 times Q plus R1. We get a quotient and remainder from the A's and the B's. And then what we do is I take these two guys, and then I do it again. So then that means Q will be Q2 plus R1 plus R2. And then I go down to the bottom when I get Q, that should be, now what are we going to get? We're going to have all these guys. These guys. So then eventually Rn minus 1 is going to be Qn times Qn minus 1 plus Rn minus 1. And then the last one is going to be 0, essentially. So what you need is, you need to use the particular solution of where, once I've done this, how do I say this is the best? What we're going to do is, using this algorithm, I'll do it with some numbers so that you can see, because I just lost everybody in the index, including myself. What I'm going to do is, I'm going to use the Euclidean Bezusian algorithm in that process that I just showed you. I'll do it with numbers because it's better. Variables and letters and stuff, and they should never the twain shall meet. Yes, they should, but in that's the justification of this process. What I'm going to do is I'm going to write, because the GCD of P and Q is 1, I can write these as linear combinations of each other. So I can find, using the Euclidean Bezusian algorithm, S and T, where I can do this because the GCD of these two is 1. I go down that and I backtrack up because the GCD was 1. I can write them as a linear combination of each other. This is also how you solve the Enigma machine in a different way, because I have to find inverses modulo m. Now what I'm going to do is I need a particular solution. So I wanted a solution to Px plus Qy equals R. So what can I do? Multiply both of these by R. Both sides by R. And now do you see what that gave me? And that is, there's my particular solution. So my y particular, my x particular, and my y particular is, I never remember what I call it, Rs and Rt. And therefore the general solution to all linear Diophantine equations in 2 variables is negative qk plus Rs, and y, is equal to the homogeneous pk plus Rt. Let's see that happen with the numbers I just picked arbitrarily. So let's do this with 8x plus 6y equals 4. We'll use small numbers. No. I'll use the 4 still. this has to be related. There's 26 letters in the alphabet, and 17 has an inverse. The Euler-Phi function, which is another arithmetic function, tells me how many. There should be 12 numbers less than 26, which are relatively prime to 26, and 17 has an inverse also. Shh, that's the Enigma machine, but I'm picking those numbers because of that. So 26 is, oh crap. 1 times 17 plus 9, please? Yes. Wait, I was finger numbering it. Number finger 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Duodecimal system. Uh-oh. 17 is, oh, it's going to be a palindrome. I didn't want that, but okay. 17 is 1 times 9 plus 8. 9 is 1 times 8. It's a palindrome. It's the same upside down, but I picked the numbers arbitrarily plus 1. And then now do you see, Saglibla, 8 is 8 times 1 plus 0. So the penultimate remainder, the last non-zero remainder, is the GCD. So I don't have to reduce, but the GCD is 1. And now watch how I do this. What you want to do is, I tell my 160 students, cancel this off, and then I need this, and it was a palindrome. On your exam, I'm not giving you a palindrome, but you have to go back up. Bezier goes back up this way. So if you color code, it's that one you use first, and then give me another one, and then this one, and then that one. That's how you can tell how the ones are different. So now I'm going to use the mathematical table, and then I'll explain one time why this works. So what you do is you write out this, you write no, no, and then I needed 3 of them. So you can do this. I need a 0 and a 1, and then you do minus, plus, minus. I said minus, plus, minus. This will be on the 26. And yeah, this will be on the 17. So now what did I say? Uh-oh. 1, 1, 1. No. Blue I was using. Blue. I'm like, wait a second. I just confused myself with the colors. Colors. No, 3 times is definitely. Now what you, oh, we can cut, let's color code that now, okay. This is going to be 1 times 1 plus 0 is 1. Then you do 1 times 1 plus 1 is 2. Oh, we're going to get Fibonacci. Fibonacci. 1 times 2 plus 1 is 3. 0, 1, 1, 2, 3. These are Fibonacci numbers. Shh, 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 shh. That's a different day. Now what does that say? 2 times 26, which is 52, minus 3 times 17, which is 51, does equal 1. And then what's a particular solution? What was my original Diophantine equation? It was 26x plus 17y equals 4. So r is 4 because I didn't have to reduce. So we multiply by 4. Uh-oh. Oh, that's going to be good. I want to keep the 26 and I want to keep the 17. 2 times 2, no, 2 times 4 is 8. I can do that. 4 times this is plus negative 12 equals 4. So I just found a particular solution. X particular is now what? 8 times 12. And so the homogeneous solution I didn't solve, but that's going to be what? If this is 0, this is 26. X equals negative 17y. So that says 26 times negative 17k. So X is equal to negative 17k plus 8, and y is equal to 26k plus negative 12. That's how you solve linear Diophantine equations. Please support us on Patreon. I'm talking myself out of a job every time I go up in front of my lectures. I've talked myself out of a job, I'm pretty sure. And the rope is short. The rope is short. So please help me. Yeah, Patreon, Patreon, Patreon. Support a wizard. Support the wizard friends. Support the School of Wizardry. What's that guy's name? That annoying freaking wizard that was fucking Harry Potter ain't got shit on me.
On that note.